They broke the rules of physics, or so it seemed. In two underground facilities separated by 3,000 kilometers, laser beams suddenly shifted by less than 1/10,000th the width of a proton. It was the faintest tremor imaginable. But the computers knew exactly what it meant. 7 billion light-years away, two impossible objects had just collided. Within hours, as scientists analyzed the signal, a creeping realization set in. Something was profoundly wrong. The data revealed two black holes, each weighing more than 100 times the mass of our Sun. But black holes of that size cannot exist. Not according to 50 years of established stellar physics. Not according to the mathematics we've tested and refined for decades. Stars massive enough to create such black holes are supposed to explode with such violence they leave nothing behind. No remnant, no core, nothing that could collapse into a black hole. We call it pair instability. The physics is unambiguous, grounded in basic quantum mechanics. We've modeled it extensively. We've observed its effects in supernova data. And that physics says, with certainty, that these black holes should not exist. Yet here was the signal. Clear, unmistakable. Two forbidden objects, spinning at nearly the maximum rate the laws of physics allow, had just merged in the most violent collision the universe can produce. The energy they released in 1 second exceeded the light output of every star in the observable universe combined. Scientists stared at their screens, checked the instruments, ran the analysis again. The signal remained. The impossible had happened. They called it GW31123, and hidden within its brief chirp was a secret about the nature of discovery itself. A secret we're about to uncover together. Welcome to Sleepable Science. Tonight, we're not just exploring black holes. We're investigating a mystery that's unfolding right now in real time, as astrophysicists around the world try to explain the unexplainable. We're going to journey from the most basic question, what is a black hole, through the violent deaths of massive stars, into the mathematics that said these particular black holes couldn't exist, and finally, to the elegant solution that was hiding in plain sight all along. But this story has a twist, a reveal that changes everything we thought we knew. And we'll get there together, following the evidence, step by step. For now, though, let yourself settle. Find a comfortable position. Let the day's tension slip away. Your breathing can slow, your thoughts can drift. Because tonight's exploration moves at the pace of cosmic time itself, unfolding slowly, revealing its secrets with patience. If these calm, curious explorations through the universe help you unwind, or if they give you a peaceful way to rest at the end of your day, consider subscribing to the channel. It helps others find their way here too, one sleepy soul seeking science at a time. Now, let's begin our journey into darkness. Let's discover what happens when gravity becomes so extreme that even light cannot escape. And let's solve the mystery of the black holes that shouldn't exist. Let's talk about black holes. What is a black hole? The fundamentals imagine standing at the edge of an enormous well. Not a well of water, but a well of gravity itself. The deeper the well, the harder it becomes to climb out. Near the top, you could escape easily. A little deeper, you'd need to run. Deeper still, you'd need a rocket. But somewhere, at some critical depth, even moving at the speed of light wouldn't be enough. You would be trapped, forever falling, never to return. That's a black hole. At its most basic level, a black hole is a region of space-time where gravity has become so intense that nothing, not matter, not energy, not even light itself, can escape from within a certain boundary. That boundary, that point of no return, has a name that feels almost poetic in its finality. The event horizon. To understand why black holes exist, we need to think about mass and space in a way that defies our everyday intuition. Take the Earth. It has a certain amount of mass, roughly 6,000 trillion kilograms, spread across a sphere about 12,700 kilometers in diameter. The gravity at Earth's surface is strong enough to keep us firmly planted on the ground, but nowhere near strong enough to trap light. A rocket traveling at about 11 kilometers per second, the escape velocity can leave Earth entirely and journey into space. Now imagine taking all of Earth's mass and compressing it, squeezing it down, shrinking it into a smaller and smaller volume. As you do this, something fascinating happens. The gravity at the surface, where you're standing at the edge of this compressed sphere, gets stronger, much stronger, because you're now closer to all that mass, and gravity's pull increases dramatically with proximity. Keep compressing, keep shrinking. Eventually, you reach a point where the escape velocity at the surface equals the speed of light. For Earth, that would happen when all our planet's mass was compressed into a sphere about 9 millimeters across, the size of a marble. At that point, Earth would become a black hole. This critical size, where escape velocity equals light speed, is called the Schwarzschild radius, named after Karl Schwarzschild, the German physicist who first calculated it in 1916, just months after Einstein published his theory of general relativity. Schwarzschild was serving in the German army during World War I when he made this discovery, solving Einstein's equations while stationed on the Russian front. He sent his solution to Einstein, who was astonished. Here, buried in the mathematics of curved space-time, was the prediction of something extraordinary, a region where gravity became so extreme that it sealed itself off from the rest of the universe. For our Sun, the Schwarzschild radius is about 3 kilometers. Pack all the Sun's mass, about 330,000 times Earth's mass, into a sphere 6 kilometers across, and you'd have a solar mass black hole. For more massive objects, the radius scales proportionally. A black hole 10 times the Sun's mass would have an event horizon 30 kilometers across. A black hole 100 times the Sun's mass would have an event horizon 300 kilometers wide. But here's where it gets deeply strange. A black hole isn't really an object in the traditional sense. It's not made of atoms or particles. It's better thought of as a feature of space-time itself, a place where the fabric of reality has been warped so severely that it forms a one-way membrane. Cross the event horizon, and you haven't hit anything solid. You've simply passed into a region from which return is impossible. Not difficult, not unlikely, impossible. A fundamental feature of how the universe works. From the outside, a black hole appears as a sphere of perfect darkness. The event horizon marks the surface of this darkness, though it's not a physical surface you could touch. It's more like a mathematical boundary, a line drawn in the geometry of space-time. Nothing can be seen beyond this line because no light from within can reach us. It's the ultimate black body, absorbing everything that falls in, reflecting nothing, revealing nothing of what lies inside. At the very center of a black hole, according to general relativity's mathematical predictions, sits what theorists call the singularity. Based on our current understanding, this would be where all the mass has collapsed to, a point of zero volume and infinite density. However, we must be careful here. When our equations produce infinities, this often signals we've reached the limits of the theory rather than describing physical reality. The singularity may represent a real physical structure, or as many physicists suspect, it may be a sign that our theories are incomplete, that we need a deeper understanding, perhaps one that unites general relativity with quantum mechanics to describe what's really there. For now, the singularity remains hidden behind the event horizon, forever sealed away from observation. And perhaps that's fitting. Some mysteries, it seems, the universe prefers to keep to itself. Between the singularity and the event horizon lies a region of extreme space-time curvature. Here, the geometry is so warped that time itself behaves in ways that seem paradoxical. From far away, if you could somehow watch an object falling toward a black hole, you would see it slow down as it approached the event horizon. Time itself appears to dilate, stretched by gravity. The falling object would appear to freeze at the horizon, its light shifting redder and redder, fading but never quite disappearing. It would seem to hover there eternally, suspended at the edge of darkness. But from the perspective of the falling object, the experience is very different. Time passes normally. There's no moment where you feel yourself slowing down. You cross the horizon at a definite moment, and once across, your fate is sealed. All paths lead inward. Trying to escape would be as futile as trying to travel backward in time. The black hole's gravity hasn't just created a steep well, it has fundamentally altered the structure of space-time so that all future directions point toward the singularity. This is what physicist Kip Thorne once described as the ultimate prison. A place you can enter but never leave. A one-way journey into a region where the normal rules cease to apply. And yet, despite this darkness, despite this sealed-off nature, black holes are not invisible to us. They reveal themselves through their effects on everything around them. Matter falling toward a black hole doesn't simply disappear quietly. It shines, it screams, it announces the black hole's presence with some of the most brilliant light in the universe. The anatomy of a black hole. If a black hole itself emits no light, how do we see them? How do we know they exist? The answer lies not in the black hole itself, but in everything it touches, everything it pulls, everything it destroys on its way to oblivion. When matter, whether gas, dust, or even entire stars, ventures too close to a black hole, it begins to fall inward. But rarely does this matter plunge straight in. Instead, conservation of angular momentum causes it to spiral, forming a vast rotating disk called an accretion disk. Think of water circling a drain, but on a cosmic scale, and with consequences far more extreme. In this accretion disk, material orbits the black hole at tremendous speeds, sometimes reaching significant fractions of the speed of light. As particles jostle and collide within the disk, friction generates heat. Enormous heat. The inner regions of an accretion disk around a stellar mass black hole can reach temperatures of millions of degrees Celsius. At these temperatures, the disk doesn't glow with visible light. It blazes with X-rays, high-energy radiation that telescopes like NASA's Chandra X-ray Observatory can detect. These X-ray emissions are often the first clue that a black hole is present. Astronomers scan the sky looking for sources of intense X-ray radiation, particularly those that seem to orbit an invisible companion. Many stellar mass black holes have been discovered this way, in binary systems where a black hole and a normal star orbit each other. The black hole steadily pulls gas from its companion, creating an accretion disk, which glows brilliantly in X-rays even as the black hole itself remains dark. But the accretion disk is only part of the story. In some black holes, something even more remarkable happens. Some of the material being drawn toward the event horizon doesn't fall in. Instead, it's redirected, channeled by powerful magnetic fields into two narrow jets that blast away from the black hole's poles at nearly the speed of light. These relativistic jets can extend for thousands of light years, streaming out into space like cosmic fountains turned upside down. How this happens is still not fully understood. The process seems to involve the interaction between the spinning black hole, the accretion disk, and the magnetic fields threading through the inflowing gas. As the disk rotates and the black hole spins, these magnetic fields become twisted and amplified, creating a kind of cosmic particle accelerator right at the edge of the event horizon. Material caught in these fields is flung outward with extraordinary violence. These jets are some of the most energetic phenomena in the entire universe. When pointed directly at Earth, they can appear as blazingly bright sources called blazers, some of the most luminous objects we can observe. The energy output from such jets can rival or exceed the entire light output of a galaxy full of stars, all driven by the gravitational power of a single black hole. Closer still to the event horizon, within just a few Schwarzschild radii, lies a region that scientists call the plunging region. Here, the black hole's gravity is so strong that even matter moving at orbital speeds can no longer maintain a stable orbit. It's the last stop before the event horizon, a zone where everything, inevitably, falls in. Recent observations have confirmed this plunging region exists exactly as Einstein's equations predicted, another triumph for general relativity. Around the black hole's event horizon, light itself behaves in extraordinary ways. Photons, particles of light, can actually orbit a black hole, trapped in unstable circular paths. This creates something called a photon sphere, a spherical surface where light circles the black hole endlessly, neither falling in nor escaping. If you could somehow stand at this distance and look sideways, you'd see the back of your own head, as light travels all the way around the black hole to return to you. For rotating black holes, those that spin, the situation becomes even more complex. The spinning black hole drags space-time itself around with it, an effect called frame dragging. This creates a region called the ergosphere, a zone outside the event horizon where nothing can remain stationary. Everything must rotate in the same direction as the black hole, carried along by the churning of space-time itself. The faster a black hole spins, the more energy is locked in its rotation. There's a theoretical maximum spin rate, where the event horizon would be rotating at the speed of light. Beyond this limit, the black hole would have no event horizon at all, exposing the singularity to the outside universe, what's called a naked singularity. Most physicists believe such objects cannot exist, protected by what's called cosmic censorship, the idea that nature always hides singularities behind event horizons. But we don't know for sure. When we observe black holes through gravitational waves, a topic we'll explore more deeply later, we can actually measure how fast they're spinning. The shape of the signal, the pattern of ripples in space-time, encodes information about the black hole's mass and spin. Some of the black holes detected by LIGO have been spinning at 70, 80, even 90% of the maximum rate. They're rotating hundreds of times per second, entire stellar masses whirling faster than any object has a right to spin. And when two such monsters meet, when they spiral together and merge, the spin of the final black hole depends on how the original black holes were oriented. If they were spinning in the same direction and their spins aligned, the final black hole spins faster. If they were misaligned or counter-rotating, the final spin is lower. This is one of the clues scientists use to understand how black holes form and how they came together. But all of this, the accretion disks and jets and spinning horizons, describes what happens outside the black hole. What about inside? What happens once you cross that boundary? The honest answer is we don't know for certain. Not yet. Once past the event horizon, the equations of general relativity predict a one-way journey toward the singularity. Based on this framework, tidal forces, the difference in gravitational pull between your head and your feet, would grow stronger and stronger. For stellar mass black holes, our models suggest these forces would tear you apart long before you reached the horizon, a process gruesomely nicknamed spaghettification. For supermassive black holes, the ones millions or billions of times the mass of the Sun, the mathematics indicates that tidal forces at the horizon would actually be quite gentle. You could, in theory, cross it without feeling anything unusual at all, though your fate would still be sealed. What awaits at the singularity remains one of the great unsolved problems in physics. The equations predict a place where density becomes infinite, where space-time curvature becomes infinite, where the classical laws break down entirely. Most physicists believe that quantum effects, currently not included in our understanding of black holes, must become important near the singularity. Perhaps quantum gravity, if we ever develop such a theory, will resolve these infinities and reveal what's really there. For now, the singularity remains mysterious, hidden, unknowable, a secret the universe keeps locked behind an impenetrable wall of gravity. The birth of black holes. Stellar death. Black holes don't appear from nothing. They have origins, births, moments of creation. And for most black holes, that moment comes at the end of a star's life, in the most violent explosions the universe can produce. Stars are furnaces. For millions or billions of years, depending on their mass, they burn steadily, fusing hydrogen into helium in their cores. The energy released by this fusion creates an outward pressure that balances the inward pull of the star's own gravity. It's a delicate equilibrium, a tug-of-war between gravity trying to crush the star and fusion trying to blow it apart. For most of a star's life, these forces balance perfectly, and the star shines peacefully into space. But nuclear fuel doesn't last forever, and when it runs out, everything changes. For stars like our Sun, relatively modest in mass, the end is gentle. As hydrogen in the core becomes depleted, the core contracts and heats up, eventually igniting helium fusion. The star swells into a red giant, puffing off its outer layers into beautiful shells of gas called planetary nebulae. What remains is a white dwarf, a dense Earth-sized ember supported not by fusion, but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too close together. White dwarfs cool and fade over trillions of years, but they never collapse further. They're the final state for stars like the Sun. But for stars much more massive, stars 10, 20, 50 times the mass of the Sun, the story is very different. These massive stars burn through their fuel much faster, living only a few million years instead of billions. And they don't stop at helium. As each fuel source exhausts, the core contracts, temperature rises, and a new fusion reaction ignites. Helium fuses to carbon and oxygen, carbon to neon and magnesium, neon to oxygen and magnesium, oxygen to silicon and sulfur, and finally, silicon fuses to iron. Iron is where the road ends. Fusing iron requires energy rather than releasing it. Once a massive star's core turns to iron, no more fusion reactions can occur. The core has reached the end of the line, and without fusion to provide outward pressure, disaster is imminent. The iron core of a massive star is incredibly dense, about the density of an atomic nucleus, but it's still held up by electron degeneracy pressure, the same quantum mechanical force supporting white dwarfs. There's a theoretical limit, though, to how much mass this pressure can support. That limit, called the Tolman-Oppenheimer-Volkoff limit, or TOV limit, is estimated to be around 2 to 3 times the mass of the Sun, though the precise value depends on the equation of state of nuclear matter at extreme densities. Once the iron core exceeds this critical mass, electron degeneracy pressure can no longer hold it up. What happens next occurs in less than a second. The core collapses catastrophically. Electrons are forced into protons, creating neutrons and releasing neutrinos. The density skyrockets. The collapse only stops when the matter becomes so dense that neutrons themselves can't be compressed further, a state called neutron degeneracy. The infalling core smashes into this incompressibly dense inner region and rebounds, sending a shockwave racing outward through the rest of the star. This shockwave, strengthened by the torrent of neutrinos flooding outward from the core, blows the star apart in a supernova explosion so bright it can briefly outshine an entire galaxy. The star's outer layers, enriched with heavy elements forged in the explosion, are scattered into space, eventually becoming the raw material for new stars, new planets, new worlds. Every atom of iron in your blood, every atom of calcium in your bones was created in such an explosion billions of years ago and scattered across the cosmos to eventually become part of you. But what about the core? What remains after the explosion? If the remnant core's mass is below the TOV limit, roughly 2 to 3 solar masses, neutron degeneracy pressure can support it, and what forms is a neutron star. These are among the densest objects in the universe, packing 1 to 2 solar masses into a sphere only about 20 kilometers across. A teaspoon of neutron star material would weigh as much as Mount Everest. However, if the remnant core is more massive than the TOV limit, then current physics suggests nothing can stop the collapse. Not electron degeneracy, not neutron degeneracy. No known force in nature can resist the inward pull of gravity at such extreme densities. The core continues collapsing, shrinking past the Schwarzschild radius, and disappears behind an event horizon. A black hole is born. This process creates what we call stellar mass black holes, typically ranging from about 3 to 20 times the mass of the Sun. These are the black holes formed directly from the deaths of individual massive stars. They're scattered throughout galaxies, silent and dark, revealed only when they interact with their surroundings. In our Milky Way galaxy alone, astronomers estimate there may be 10 million to 100 million stellar mass black holes. Most orbit silently through space, invisible, detectable only through their gravitational influence on nearby stars or gas clouds. Occasionally, we get lucky. A black hole in a binary system pulls matter from its companion star, creating an accretion disk that blazes in X-rays. Or two black holes, long ago paired in a binary, finally spiral together and merge, sending gravitational waves rippling across the universe. Since 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, made its first detection, we've observed hundreds of such mergers. Each one provides a new data point, a new piece of evidence about how black holes behave, how they form, what masses they come in. And slowly, a picture has been emerging. A picture that includes some surprises, some mysteries, some black holes that, by all rights, shouldn't exist at all. Which brings us back to our impossible collision. To understand why GW223-11123 was so shocking, why those two black holes shouldn't exist, we need to talk about the mass gap, the forbidden zone. The range of masses where theory says black holes simply cannot form through stellar collapse. The forbidden zone, the mass gap. There's a problem with very massive stars. A problem that, until recently, we thought we understood completely. That problem has to do with what happens when you try to make a black hole heavier than about 60 times the mass of the Sun through the usual process of stellar collapse. It doesn't work. At least, it shouldn't work. And here's why. Remember that stellar mass black holes form when the iron core of a massive star collapses. The core needs to be more massive than the TOV limit, around 2 to 3 solar masses, for the collapse to proceed all the way to a black hole instead of stopping at a neutron star. But the core's mass doesn't directly translate to the final black hole's mass in a simple way, because of what happens during the supernova. For stars that are very, very massive, with cores approaching or exceeding about 60 solar masses, something extraordinary happens during the final stages of their lives. The temperatures and energies in the core become so extreme that a new process kicks in, one that destabilizes the entire star. It's called pair instability, and it's one of the most violent processes in stellar evolution. At temperatures nearing several hundred million degrees Celsius, something remarkable occurs. Photons, particles of light, carry so much energy that they can spontaneously transform into particle-antiparticle pairs. Specifically, electrons and positrons, the antimatter version of electrons, materialize from the energy of the light itself. This is pair production, allowed by the equivalence of mass and energy described by Einstein's famous equation E equals mc squared. Under normal circumstances, this wouldn't be a big deal. But in the core of a very massive star, pair production becomes a runaway process. Here's why. Those photons were providing pressure, helping to hold the star up against gravity. When photons turn into particle pairs, that pressure support suddenly drops. With less pressure, the core contracts. When the core contracts, temperature rises. When temperature rises, even more pair production occurs. And so on, in a rapid feedback loop. This is called pair instability, and it leads to catastrophic consequences. As the core loses pressure support, it begins to collapse. But unlike the controlled, inevitable collapse that forms a black hole, this collapse triggers violent thermonuclear fusion of the remaining unburned material. The star doesn't implode quietly. It explodes. Completely. No remnant is left. No black hole forms. The entire star, including the core, is blown to smithereens, scattered into space as gas and dust. Nothing remains to become a black hole. Astrophysicists have calculated this process extensively using sophisticated stellar evolution codes. For stars with cores in the mass range of about 60 to 130 solar masses, pair instability is expected to destroy the star entirely, preventing black hole formation. This creates what's known as the pair instability mass gap, or simply the black hole mass gap. Black holes in this range shouldn't exist if they formed from single-star collapse through the standard process. Below approximately 60 solar masses, cores can collapse to form black holes, though the exact lower boundary of the gap remains somewhat uncertain and may depend on factors like the star's rotation rate, metallicity, and, as we'll discover, other physical processes that affect stellar evolution. Above about 130 to 135 solar masses, stars are so massive that even pair instability can't completely disrupt them. They collapse directly to black holes, bypassing the pair instability phase entirely. But in that middle range, that forbidden zone, theory based on standard stellar evolution models has been clear. No black holes should form. This wasn't just speculation. The physics of pair instability is well understood, grounded in basic quantum mechanics and relativity. Multiple independent research groups using sophisticated stellar evolution codes all came to the same conclusion. However, as with all complex models, these simulations necessarily made certain simplifications to remain computationally tractable. And sometimes, what seems like a reasonable simplification can hide crucial physics. We'll return to this idea. Then came gravitational wave detections. Then came LIGO. And then came the surprises that would force us to question our assumptions. The first hint that something was off came in May 2019 with an event called GW90521. LIGO detected gravitational waves from the merger of two black holes with masses of approximately 66 and 85 solar masses. Both fell squarely in the mass gap. Both shouldn't exist according to standard models. The final merged black hole weighed in at about 142 solar masses, with 9 solar masses of energy radiated away as gravitational waves during the collision. This was puzzling, but not impossible to explain within existing frameworks. The leading theory was that these black holes didn't form from individual stars. Instead, they formed hierarchically. Perhaps two smaller black holes, safely below the mass gap, merged to form a medium-mass black hole. Then that black hole merged with another, and so on, building up mass through successive generations of mergers. In dense star clusters, or in the chaotic environments near galactic centers, such hierarchical mergers might happen frequently enough to explain the observations. It was a satisfying explanation. Hierarchical mergers could produce black holes in the mass gap without violating the physics of stellar collapse. The mass gap for single star formation could still exist. The simplifications in our models could remain justified. Scientists were confident they had resolved the mystery. But what if the universe was trying to tell us something else? What if these detections weren't exotic exceptions requiring special environments and multiple generations of mergers? What if they were pointing to something we'd overlooked in the fundamental physics of how massive stars die? Then came GW33123, and the explanations started to crumble. Because GW2311123 wasn't just one black hole in the mass gap. It was two. Two impossibly massive, impossibly rapidly spinning black holes, both deep in the forbidden zone, and both displaying characteristics that hierarchical mergers struggle to explain. The detected event involved black holes with masses of approximately 100 and 140 solar masses. These aren't just nudging the edge of the mass gap. They're planted firmly in the middle of it, and they were spinning at around 80 to 90% of the maximum rate allowed by physics. They were rotating faster than almost any black hole LIGO had ever confidently measured. Here's where the hierarchical merger explanation begins to strain under closer examination. When two black holes merge, the spin of the resulting black hole depends on the spins and orientations of the progenitors. If the two black holes are spinning in opposite directions, or at awkward angles to each other, the spins partially cancel out. The final black hole ends up with a relatively slow spin. To get a very rapidly spinning black hole from a merger, you need the progenitor black holes to be spinning rapidly and well aligned. But hierarchical mergers, especially those happening in dense stellar environments with lots of random encounters, tend to produce black holes with more random spin orientations. Statistical models suggest that getting two black holes, both massive and both rapidly spinning and both properly aligned, through hierarchical mergers alone is possible, but the probability decreases significantly with each additional requirement. The more scientists examined GW2311123's properties, the more the evidence pointed away from simple hierarchical formation. This suggested these black holes had formed some other way, perhaps directly through a process that could bypass pair instability. For months after the detection, teams of astrophysicists worked to solve the puzzle. Computer simulations ran for thousands of hours. New ideas were proposed, tested, refined. The forbidden black holes had been found, but how they came to be remained a mystery. Some researchers proposed these black holes formed in the accretion disks around supermassive black holes, where they could grow rapidly by consuming gas. Others suggested exotic processes involving dark matter. A few even wondered whether we needed new physics beyond the standard model. But the answer, when it finally came, didn't require exotic environments or new fundamental physics. It required something simpler and more profound. Looking at the old equations without the simplifications. Taking seriously something that had been there all along but treated as a minor detail. Until, in late 2025, a team led by astrophysicist Ore Gottlieb at the Flatiron Institute's Center for Computational Astrophysics finally found the answer. And it was elegant, surprising, and it had been hiding in plain sight all along, waiting for someone to look at the complete physics with fresh eyes and sufficient computing power. The solution would reveal something profound, not just about black holes, but about the nature of scientific discovery itself. But to understand it, we first need to step back and understand how we detected these objects in the first place. Gravitational waves, Einstein's prediction. To understand how we detected these forbidden black holes, we need to step back and talk about the messenger that carried their story across the universe. We need to talk about gravitational waves, one of the strangest and most beautiful predictions ever to emerge from theoretical physics. The story begins in 1915, when Albert Einstein published his general theory of relativity. This theory revolutionized our understanding of gravity. For centuries, going back to Isaac Newton, gravity had been thought of as a force, an invisible pull between masses. Newton's laws worked remarkably well, accurately predicting the motions of planets, the paths of projectiles, even the existence of undiscovered planets inferred from the orbits of known ones. But Einstein showed that gravity isn't a force at all, at least not in the traditional sense. Instead, mass and energy curve the fabric of space-time itself. Objects move along the straightest possible paths through this curved geometry. What we perceive as gravity, the Earth orbiting the Sun or an apple falling from a tree, is actually objects following geodesics, the natural paths through curved space-time, much like how a marble rolling across a stretched rubber sheet would follow the curves and dips created by a heavy ball placed on the sheet. General relativity made predictions that Newtonian gravity couldn't. It explained the anomalous precession of Mercury's orbit, a tiny discrepancy that had puzzled astronomers for decades. It predicted that starlight would bend when passing near the Sun, a prediction famously confirmed during a solar eclipse in 1919, making Einstein an international celebrity almost overnight. And it predicted gravitational waves. If space-time itself is a dynamic, flexible fabric that can be curved by mass and energy, then ripples should be able to travel through it. When massive objects accelerate, particularly when they orbit or collide, they should create waves that propagate outward at the speed of light, alternately stretching and squeezing space itself as they pass. Einstein himself was unsure whether gravitational waves were real or just mathematical artifacts. He published papers arguing both sides. The question wasn't fully resolved until the 1960s and 70s, when physicists like Joseph Weber, Kip Thorne, and others laid out the theoretical framework more rigorously. Gravitational waves, they confirmed, should indeed be real, but they would be incredibly weak. How weak? Consider two black holes, each 30 times the mass of the Sun, orbiting each other at a distance of a few hundred kilometers, just moments before they merge. This is an incredibly violent event, releasing more power in a fraction of a second than all the stars in the observable universe combined. And the gravitational wave signal produced by this collision, by the time it reaches Earth from a distance of 1 billion light-years, would stretch and squeeze space by about 1 part in 10 to the 21st power. 1 part in 1 billion trillion. To put that in perspective, if you tried to measure this distortion in the distance between Earth and the nearest star, Proxima Centauri, about 4 light-years away, you'd be looking for a change smaller than the width of a human hair. Einstein thought such waves would be impossible to detect. The technology simply didn't exist. But over the decades, physicists refused to give up. If gravitational waves were real, and if they could be detected, they would open an entirely new window onto the universe. They would let us observe events that emit no light. They would let us probe regions where gravity is so extreme that light cannot escape. They would let us test general relativity in its most extreme regime, where space-time curvature is strongest. The effort to detect gravitational waves became one of the most ambitious projects in the history of science. It required developing new technologies, new materials, new ways of isolating detectors from every possible source of noise, from seismic vibrations to quantum fluctuations. The breakthrough came with LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO consists of two identical facilities, one in Hanford, Washington, and one in Livingston, Louisiana, separated by about 3,000 kilometers. Each facility is an L-shaped detector with arms 4 kilometers long. At the corner of the L, a laser beam is split and sent down each arm. The beams bounce off mirrors at the ends of the arms and return to recombine. Under normal circumstances, the arms are exactly the same length, and the beams recombine in a specific way. But when a gravitational wave passes through, it stretches space in one direction while squeezing it in the perpendicular direction. One arm of the detector becomes slightly longer, while the other becomes slightly shorter. Then the wave's polarity flips, and the opposite happens. This stretching and squeezing causes the laser beams to go slightly out of sync. When they recombine, the interference pattern changes, and that change can be measured. The sensitivity required is almost incomprehensible. LIGO can detect changes in the arm lengths smaller than 1/10,000th the diameter of a proton. Its measuring shifts thousands of times smaller than an atomic nucleus in structures 4 kilometers long. Every possible source of noise had to be eliminated or accounted for. Earthquakes, ocean waves, logging trucks passing miles away, even quantum fluctuations in the laser light itself all had to be carefully modeled and subtracted. For years, the detectors ran in various configurations, slowly improving. Early versions running from 2002 to 2010 detected nothing. The instruments weren't sensitive enough yet. Then came advanced LIGO, a major upgrade that increased sensitivity by a factor of 10. The upgraded detectors came online in September 2015, and on September 14, 2015, just days after beginning their observing run, both detectors registered the same signal. A chirp, a rising tone that lasted only a fraction of a second but carried a universe of information. That chirp was the death spiral and merger of two black holes, each about 30 times the mass of the Sun, located more than 1 billion light-years away. The signal matched the predictions of general relativity with extraordinary precision. The masses of the black holes, their spins, the distance to the event, even the final ring-down of the merged black hole as it settled into its final shape, all could be extracted from that brief signal. GW1FINT0914, as the event was designated, was the first direct detection of gravitational waves and the first direct observation of a black hole merger. It confirmed that black holes exist, that they can exist in binary systems, and that Einstein's theory holds up even in the most extreme gravitational conditions. For this achievement, Rainer Weiss, Barry Barish, and Kip Thorne were awarded the 2017 Nobel Prize in Physics. It was a triumph of human ingenuity, persistence, and faith in the power of mathematical physics to describe reality. Since that first detection, LIGO has been joined by Virgo, a similar detector in Italy, and Kagra, a detector in Japan. Together, the LIGO-Virgo-Kagra collaboration, LVK, has detected hundreds of black hole mergers, along with neutron star mergers and even mixed events where a black hole collides with a neutron star. Each detection adds to our understanding. Each gravitational wave signal carries information that simply cannot be obtained any other way. The frequencies and amplitudes encode the masses and spins of the merging objects. The rate at which the frequency increases tells us how quickly they're spiraling together. The final ring-down, a brief damped oscillation as the merged black hole settles, reveals the properties of the final object. For GW2323, detected on November 23, 2023, the signal was brief but powerful. The two massive black holes were orbiting each other at a significant fraction of the speed of light, warping spacetime around them into wild, churning patterns. As they spiraled inward, they radiated gravitational wave energy, losing orbital energy and falling closer together. The frequency of the waves increased, a cosmic chirp rising in pitch. Then, in a final fraction of a second, the black holes merged. Their event horizons touched and coalesced into a single, larger horizon. The collision was so violent, so energetic, that it sent shudders through space-time detectable across billions of light-years. The merged black hole, now weighing about 225 solar masses, was left spinning rapidly and vibrating, like a bell that's been struck. These vibrations, called quasi-normal modes or ring-down modes, have specific frequencies determined entirely by the black hole's mass and spin, nothing else. By measuring these frequencies, scientists could confirm that the final object was indeed a black hole, behaving exactly as general relativity predicts. This ring-down observation, made with unprecedented clarity in another massive merger detected earlier in 2025, called GW2550144, confirmed predictions made decades ago by physicists including Roy Kerr and Stephen Hawking. It showed that black holes are, as physicist John Wheeler once said, the simplest macroscopic objects in the universe, characterized entirely by their mass, spin, and electric charge, with no other properties, no hair. But what made GW23123 extraordinary wasn't just that we detected it, though that alone was remarkable. It was what the signal told us about the black holes themselves, their masses, their spins, the mystery of how they came to exist. A mystery that would require new physics, new ideas, and a fundamental rethinking of how massive stars die. The 2023 discovery, GW2231123 in detail. November 23, 2023 was a Thursday. For most people, it was an ordinary day. But in two facilities separated by thousands of miles, in the underground tunnels of LIGO's detectors, something extraordinary registered. A whisper from the deep. A signal that would challenge everything we thought we knew about stellar death and black hole formation. The gravitational wave arrived at 11:02 and 16 seconds UTC. It passed through Earth, briefly stretching and squeezing space itself, causing the mirrors in LIGO's 4-kilometer arms to shift by distances far smaller than an atomic nucleus. The entire signal, from first detection to the final merger, lasted less than 1 second. In that fraction of a second, two objects each weighing more than 100 suns, orbiting each other at speeds approaching that of light, came together in the most violent collision the universe can produce, and the ripple from that collision, traveling for 7 billion years across an expanding cosmos, was still strong enough when it reached Earth to move those mirrors by 1/10,000th the width of a proton. Think about that for a moment. 7 billion light years. The light that left that collision when the universe was roughly half its current age, when our Milky Way was still forming its disk, when the atoms that would one day become Earth and everything on it were scattered across space. And still, we felt it. Not with our hands or our eyes, but with instruments so sensitive they seemed to border on the impossible. Scientists call it a chirp, and that's exactly what it sounds like if you convert the gravitational wave signal to audio frequencies. A rapid upward sweep in pitch, rising from about 50 Hz to several hundred Hz in a fraction of a second, then cutting off abruptly. That chirp encodes an entire story. Two massive objects in orbit, spiraling inward, moving faster and faster, radiating energy as gravitational waves, until they finally collide and merge into one. But it was what came after the initial detection, during the careful analysis, that would make this event extraordinary. It was in the details extracted from that brief signal that the impossibility would become clear. The data streamed in from multiple detectors. LIGO Hanford in Washington, LIGO Livingston in Louisiana, Virgo in Italy. Each detector had registered the same signal, arriving at slightly different times due to the finite speed of gravitational waves. By comparing these arrival times and the signal characteristics at each location, scientists could reconstruct the direction in the sky from which the waves came, though not precisely enough to pinpoint a specific galaxy. Then came the analysis. Complex algorithms compared the detected signal to vast libraries of theoretical templates, simulations of what gravitational waves from different types of mergers should look like. The best match came from a model of two spinning black holes spiraling together, but the estimated masses kept coming out surprisingly large, much larger than typical. As more sophisticated analysis techniques were applied over the following weeks and months, the picture became clearer and more puzzling. The event, designated GW2Q23, involved two black holes with masses of approximately 100 and 140 times the mass of the Sun, with uncertainties of roughly plus or minus 15 to 20 solar masses. The final merged black hole weighed about 225 solar masses. About 15 solar masses worth of energy, more than the mass of 15 entire suns, had been radiated away as gravitational waves during the merger. That energy release is almost incomprehensible. In the fraction of a second during which the black holes merged, they emitted more power in gravitational waves than all the stars in the visible universe combined emit in light. For that brief moment, this merger was the brightest thing in the universe, if you had eyes that could see gravitational radiation. But even more remarkable than the masses were the spins. Both black holes were rotating rapidly. The analysis indicated that one was spinning at around 80% of the maximum rate allowed by physics, while the other was at roughly 90%. For reference, the maximum spin rate for a black hole is where the event horizon itself is rotating at the speed of light. These black holes were rotating hundreds of times per second, their entire masses, each more than 100 suns, whirling faster than anything that large should be able to spin. Why does this matter? Because spin encodes formation history. How a black hole is spinning when we observe it tells us something about where it came from and what happened to it. A black hole that forms from a single collapsing star will have some spin inherited from the rotation of the progenitor star. Most stars rotate, and as they collapse, conservation of angular momentum causes them to spin faster, like a figure skater pulling in their arms. But there are limits to how fast a star can be rotating before centrifugal forces tear it apart or before mass loss slows it down. Single star formation typically produces black holes with moderate spins, rarely exceeding 50 to 70% of maximum. Hierarchical mergers, where smaller black holes collide and combine, can produce higher spins, but usually only if the colliding black holes are themselves spinning rapidly and their spins are well aligned. Random collisions between black holes with random spin orientations tend to produce final black holes with intermediate spins, not extremely high ones. The fact that both black holes in GW231123 were spinning so rapidly suggested something unusual about their formation. And their masses, deep in the pair instability mass gap, made it clear that standard stellar collapse couldn't explain them. Not by itself. Not without something extra. Some mechanism that could bypass pair instability and produce massive, rapidly spinning black holes in a single generation. This became the challenge that faced astrophysicists in late 2023 and into 2024 and 2025. How do you make a black hole that theory says shouldn't exist? How do you form a black hole weighing more than 100 times the Sun from a star, when pair instability should blow that star apart completely. Various ideas were proposed. Perhaps these black holes formed in the disks around supermassive black holes at the centers of galaxies, where densities are high and black holes can accrete mass rapidly, growing beyond the mass gap after formation. Perhaps they formed through exotic processes we haven't considered, involving dark matter or physics beyond the standard model. But the leading solution, the one that would eventually explain GWB, came from a team at the Flatiron Institute led by Ore Gottlieb, and it required going back to basics, revisiting the process of stellar collapse with fresh eyes and, critically, including something that most previous simulations had simplified or ignored entirely: magnetic fields. Solving the mystery. Magnetic fields and spinning stars throughout most of the history of theoretical astrophysics. When scientists modeled stellar collapse and black hole formation, they made simplifications. This wasn't carelessness, it was necessity. The equations governing stellar evolution are incredibly complex, involving hydrodynamics, thermodynamics, nuclear reactions, radiation transport, and more. Add in magnetic fields, which create additional forces and feedback loops, and the computational requirements become staggering. So, for decades, most models either ignored magnetic fields entirely or included them in simplified form. The focus was on gravity, pressure, and nuclear reactions, the primary drivers of stellar evolution. Magnetic fields were treated as secondary, unimportant for the large-scale structure and fate of stars. This worked well for most purposes. Models without magnetic fields successfully predicted the life cycles of stars, the types of supernova, the conditions for forming white dwarfs and neutron stars. For typical black hole formation, magnetic fields didn't seem to matter much. But for very massive stars, stars on the edge of pair instability, stars trying to collapse into black holes in the mass gap, it turns out magnetic fields change everything. Ore Gottlieb and his colleagues at the Flatiron Institute, working with researchers at institutions including Northwestern University and Columbia University, decided to include magnetic fields properly, not as a minor perturbation, but as a full dynamical component of the simulation. They modeled the collapse of rapidly rotating, massive stars with strong magnetic fields using general relativistic magnetohydrodynamics, GRMHD, some of the most sophisticated simulation codes in existence. What they found was remarkable. When a rapidly rotating massive star collapses, the infalling material doesn't just fall straight into the forming black hole. Instead, conservation of angular momentum causes it to form a rotating accretion disk around the newly born black hole. This disk is incredibly hot, incredibly dense, and threaded with magnetic fields inherited from the progenitor star. In previous models without magnetic fields, this disk would simply feed material into the black hole. All the material in the disk, everything from the collapsed core, would fall across the event horizon, making the final black hole as massive as possible. But when you include magnetic fields, something different happens. The rapid rotation of the disk, combined with the extreme conditions near the black hole, amplifies the magnetic fields through a process called the magnetar, rotational instability. The fields become tangled, twisted, and enormously powerful. These fields then drive powerful winds and jets, blasting material away from the black hole at nearly the speed of light. This is the key insight. The outflows driven by magnetic fields remove mass from the system before it can fall into the black hole. The stronger the magnetic fields, the more mass is ejected. The final black hole ends up with less mass than it would have had without magnetic fields. For stars on the edge of pair instability, this changes everything. Remember that pair instability is supposed to blow the star apart completely, leaving no remnant. But what if some of the mass is removed before pair instability fully kicks in? What if magnetic fields eject enough material that the remaining core, though still massive, avoids the worst of the pair instability phase and can collapse to a black hole? That's exactly what Gottlieb's simulations showed. For rapidly rotating massive stars with strong magnetic fields, the final black hole mass can be significantly reduced compared to the initial core mass. Stars that would normally explode completely instead form black holes, but black holes with masses reduced enough to fall within the mass gap. Even more remarkably, the simulations naturally predicted a correlation between mass and spin. Stars with moderate magnetic fields lose some mass to outflows, producing relatively massive black holes with high spins. Stars with stronger magnetic fields lose more mass, producing lighter black holes with even higher spins, because the magnetic fields also affect how angular momentum is transported and conserved. This correlation matches the observations of GW231123 beautifully. The two black holes had different masses, but both had very high spins, exactly what you'd expect if they formed through magnetic field-driven mass loss from rotating massive stars with different field strengths. The simulations made another prediction, one that could potentially be tested with future observations. When magnetic fields drive material away from a forming black hole, the models suggest they should also produce gamma-ray bursts, brief, intense flashes of high-energy light. These bursts might be detectable if we catch a massive star collapsing at exactly the right moment and angle. Finding such bursts correlated with black hole formation would provide strong support for the magnetic field model. As of late 2025, the magnetic field explanation for mass gap black holes represents the leading theoretical framework, supported by detailed simulations published in the astrophysical journal Letters. However, as with all new scientific models, it requires further testing and validation. More gravitational wave detections of similar systems will help test the predicted mass-spin correlation. Searches for associated gamma-ray bursts from stellar collapse events will help confirm the model's other signatures. The scientific community continues to analyze the data and refine the theory. What makes this explanation particularly compelling from a scientific perspective is its elegance. By including physics that had been overlooked, by taking magnetic fields seriously in their full complexity, Gottlieb and his team provided a natural mechanism for forming black holes that theory had suggested couldn't exist through standard channels. They demonstrated that pair instability isn't an absolute barrier when the full physics of rotating magnetized stellar collapse is properly considered. It's a reminder of how science works. We build models based on the best physics we understand. We make predictions. Then nature surprises us. Observations contradict expectations. And we go back to the drawing board, not to throw out the physics, but to check our assumptions, to see what we might have overlooked. Often the answer was there all along, hiding in the equations, waiting for someone to take it seriously. The mass gap black holes exist. GW231123 proved that beyond doubt. Now we know not just that they exist, but how they might form. Another mystery, solved, another piece of the cosmic puzzle fitting into place. Types of black holes across the universe. Step back for a moment and consider the full menagerie of black holes scattered across the cosmos. They come in different sizes, different masses, formed through different processes, playing different roles in the evolution of galaxies and the structure of the universe itself. From the smallest stellar mass black holes to the largest supermassive monsters, they represent one of the most diverse and fascinating populations of objects in all of astronomy. We've already discussed stellar mass black holes extensively, those ranging from about 3 to perhaps 100 solar masses, formed from the collapse of massive stars. These are the most common black holes in the universe. In our Milky Way galaxy alone, there may be 100 million of them, though most remain dark and undetected, drifting silently through space. We know they're there from statistical arguments and from the rate at which massive stars die, but we've directly detected only a tiny fraction. Most stellar mass black holes are found through X-ray emissions, when they're in binary systems with normal stars and accreting matter from their companions. About 24 such systems have been confirmed in our galaxy. Since 2015, gravitational wave detections have added hundreds more to the census, revealing black holes in binary systems that emit no X-rays, that have no visible companions, that would otherwise remain completely hidden. Then there are supermassive black holes, the giants that lurk at the centers of galaxies. These range from about 100,000 to tens of billions of times the mass of the Sun. Our own Milky Way's central black hole, Sagittarius A, abbreviated as A star, weighs about 4 million solar masses. It sits at the galactic center, 26,000 light-years from Earth, surrounded by a dense cluster of stars orbiting at tremendous speeds. Astronomers have tracked individual stars in the galactic center for decades, watching them orbit the invisible mass at the center. Some of these stars complete their orbits in just a few years, traveling at several % of the speed of light at closest approach. By measuring these orbits, scientists have determined the mass of Sagittarius A with high precision. It's definitely a black hole. Nothing else could pack 4 million solar masses into such a compact region. In 2019, the Event Horizon Telescope, a global network of radio telescopes working together as a single Earth-sized instrument, captured the first image of a black hole's event horizon. That black hole wasn't SCRE. It was M87, the supermassive black hole at the center of the elliptical galaxy Messier 87, located about 55 million light-years away. M87 weighs about 6.5 billion solar masses, more than 1,000 times more massive than Sagittarius A. The image showed exactly what general relativity predicted. A dark circular shadow, surrounded by a bright ring of light, the emission from hot gas in the accretion disk, distorted by the extreme gravity. The shadow is actually larger than the event horizon itself, created by light-bending effects that cause photons orbiting near the black hole to appear to circle the darkness. It was a triumph of observational astronomy and a stunning confirmation of Einstein's theory. Supermassive black holes appear to exist in the centers of most, if not all, large galaxies. How they formed remains one of astrophysics' most intriguing puzzles. They can't have formed simply from stellar collapse in any straightforward way. Even if you collapsed 1,000 massive stars in the same spot, you'd need some mechanism to bring them together. And observations of extremely distant, and therefore young, galaxies show that supermassive black holes existed when the universe was less than 1 billion years old, seemingly not enough time for them to have grown from stellar mass seeds through gradual accretion. Several formation scenarios have been proposed, each with supporting evidence and remaining questions. One possibility is that supermassive black holes formed from the direct collapse of enormous gas clouds in the early universe, creating massive black holes from the start. Another hypothesis suggests they formed from collisions and mergers of thousands of smaller black holes in dense star clusters. The evidence suggests that some combination of processes likely contributed, with the dominant mechanism perhaps varying from galaxy to galaxy. This remains an active area of research, with new observations from the James Webb Space Telescope now probing the earliest supermassive black holes with unprecedented detail. Between stellar mass and supermassive black holes lies an intriguing and poorly understood class: intermediate mass black holes, or IMBHs, ranging from about 100 to 100,000 solar masses. These have been predicted to exist as a bridge between the two well-established populations, but until recently, confirmed detections were rare. GW 9190521, the 2019 detection of a merger producing a 142 solar mass black hole, provided some of the best evidence yet for an IMBH. GW 231123's final black hole, at 225 solar masses, is even more clearly in this intermediate range. Whether these objects form through hierarchical mergers, through the collapse of very massive stars in the early universe, or through runaway collisions in dense star clusters remains an open question. Finding more IMBHs is a major goal of gravitational wave astronomy. If they exist in large numbers, they might help explain how supermassive black holes formed so early in the universe's history. Small IMBHs could serve as seeds that grew into supermassive ones through mergers and accretion over billions of years. There's also speculation about even smaller black holes. Primordial black holes, if they exist, could theoretically have formed in the first fractions of a second after the Big Bang, when the universe was a hot, dense soup of matter and energy. The hypothesis suggests that quantum fluctuations during cosmic inflation might have created regions dense enough to collapse directly into black holes, with masses ranging from microscopic to many times the mass of the Sun. Some researchers have proposed primordial black holes as candidates for dark matter, the invisible substance that outweighs visible matter in the universe by a factor of 5. However, so far, observational searches have found no direct evidence they exist, and various constraints have ruled out primordial black holes as the dominant component of dark matter in most mass ranges. The question remains open for investigation. At the other extreme, some physicists have speculated about whether the entire observable universe might be inside a black hole, or whether other universes might exist as black holes within our own. These ideas venture into highly speculative territory, beyond current testability. But they highlight how black holes challenge our understanding of space, time, and causality at the deepest levels. Across all these categories, from the smallest hypothetical primordial black holes to the largest supermassive monsters, black holes share common properties. They all have event horizons. They all have singularities, or at least regions where our understanding breaks down. They all curve spacetime severely. They all can grow by accreting matter and can merge with other black holes. And they all, in principle, emit Hawking radiation, though for stellar mass and larger black holes, this radiation is so weak it's utterly negligible compared to the cosmic background temperature. In a sense, all black holes are the same, at least according to what's called the no-hair theorem. This principle, developed by physicists including Werner Israel, Brandon Carter, and Stephen Hawking in the 1960s and 70s, proposes that black holes are characterized entirely by mass, spin, and electric charge. If this theorem holds, two black holes with the same mass, spin, and charge would be identical, regardless of what they're made from or how they formed. You couldn't tell if a black hole came from collapsed iron, collapsed helium, or even collapsed light. The event horizon, according to this view, erases all information about the interior. However, this leads to what's known as the information paradox, a deep puzzle where quantum mechanics seems to conflict with general relativity. Quantum mechanics suggests that information cannot be truly destroyed, yet general relativity's description of black holes seems to indicate that information falling past an event horizon is lost forever. This paradox remains one of the most profound unsolved problems in theoretical physics, with proposed solutions ranging from subtle correlations in Hawking radiation to the holographic principle, which suggests the information might be encoded on the event horizon itself. The resolution of this paradox will likely require a complete theory of quantum gravity. But these are questions for theorists. For observers, for gravitational wave astronomers, The goal is simpler. Find more black holes, measure their masses and spins, understand their populations, map how they're distributed across cosmic time. Each detection adds to our understanding. Each merger reveals a new piece of the story. The future of black hole discovery. Gravitational wave astronomy is still in its infancy. LIGO made its first detection less than 10 years ago. We've observed a few hundred black hole mergers, a few neutron star mergers, and we're just beginning to understand what the data is telling us. But the future promises so much more. More sensitive detectors, more frequent observations, new types of sources, new mysteries waiting to be uncovered. LIGO and Virgo have undergone several upgrades since their first detections, each time improving sensitivity and reducing noise. Kagra, the Japanese detector, came online more recently and is still ramping up to full sensitivity. Together, these detectors can localize gravitational wave sources to within a few square degrees on the sky, allowing optical telescopes to search for electromagnetic counterparts, flashes of light that might accompany the gravitational wave signal. The most famous example of such a multi-messenger observation came in August 2017, when LIGO and Virgo detected gravitational waves from a neutron star merger. Within seconds, gamma-ray satellites detected a short gamma-ray burst from the same direction. Within hours, optical telescopes observed a kilonova, a brilliant explosion powered by the decay of heavy elements synthesized in the merger. This event, GW 170817, confirmed that neutron star mergers are a major source of heavy elements like gold and platinum. It also provided a new way to measure the expansion rate of the universe. For black hole mergers, electromagnetic counterparts are less common. Black holes don't contain nuclear matter that can explode or glow. The mergers themselves emit gravitational waves but no light. However, if a black hole merger occurs in a dense environment, such as the accretion disk around a supermassive black hole, there might be associated flares of light as the shockwave from the merger disturbs surrounding gas. Looking ahead, several new gravitational wave detectors are planned or under construction. LIGO India, a third LIGO detector being built in India, will improve localization by providing another point in the global network. Einstein Telescope, a proposed European detector with 10-kilometer arms housed underground, would be significantly more sensitive than current detectors, capable of detecting mergers across the entire observable universe. And then there's LISA, the Laser Interferometer Space Antenna. This is perhaps the most ambitious gravitational wave project ever conceived. Instead of being built on Earth, LISA will consist of 3 spacecraft in solar orbit, forming a triangle with sides 5 million kilometers long. Free from seismic noise and able to maintain exquisite stability, LISA will detect lower-frequency gravitational waves than LIGO, waves from more massive, more slowly orbiting systems. LISA's targets would include supermassive black hole mergers, events where black holes weighing millions or billions of solar masses collide when galaxies merge. Based on our understanding of galaxy evolution, these mergers should take years to complete, and the gravitational waves would sweep through millihertz frequencies, too low for ground-based detectors, but potentially ideal for LISA. Observing supermassive black hole mergers could help us understand how galaxies evolve, how black holes grow, and how common such events are across cosmic history. LISA might also detect thousands of stellar mass black holes orbiting close to supermassive black holes, systems called extreme mass ratio in spirals, where a small black hole spirals gradually into a galactic center black hole. Current models suggest these systems can emit gravitational waves for years, which would allow extraordinarily precise measurements of the space-time geometry around the supermassive black hole, testing general relativity with unprecedented accuracy. If approved and funded, LISA is expected to launch in the mid-2030s. It represents the next generation of gravitational wave astronomy, moving from ground-based detectors to space, from stellar masses to supermassive scales, from hundreds of detections to potentially thousands per year. Other proposed detectors include Cosmic Explorer, a US concept for ground-based detectors, with 40-kilometer arms, 10 times longer than LIGO's. Such a facility could detect neutron star mergers across the entire observable universe and black hole mergers from the very first generation of stars. It would provide a census of black holes across cosmic time, revealing how their population has evolved. Pulsar timing arrays represent yet another approach. By precisely monitoring the timing of pulses from millisecond pulsars, natural cosmic clocks, astronomers can detect very low-frequency gravitational waves, nanohertz frequencies, likely from supermassive black hole binaries across the universe. Several pulsar timing arrays are now reporting evidence for a gravitational wave background, a hum of overlapping signals from countless distant mergers, though individual events remain difficult to distinguish. As detectors improve and multiply, the rate of discoveries will accelerate. We'll move from detecting the loudest, closest events to probing fainter, more distant systems. We'll build up statistical samples large enough to answer questions about black hole populations, spin distributions, merger rates, and how these properties evolve with redshift and cosmic time. Some of the questions we hope to answer in coming years include: how common are black holes in the mass gap? Do they form primarily through magnetic field-driven collapse, as recent simulations suggest, or are other mechanisms also at play? How do black hole spins depend on formation environment? Could there be primordial black holes? And if so, what fraction of dark matter might they comprise? How quickly do supermassive black holes grow, and what role do mergers play in their evolution? We might also discover entirely unexpected phenomena. Every time we've opened a new observational window onto the universe, from radio waves to X-rays to neutrinos, we've found surprises. Gravitational wave astronomy appears to be no different. Already we've seen black holes more massive than standard models predicted, mergers in configurations we didn't expect, spin distributions that challenge formation theories. The data suggests there's much more to discover. Perhaps intermediate mass black holes are common in globular clusters, ancient stellar groupings orbiting the outer reaches of galaxies. Perhaps there are black holes in extremely tight binaries, spiraling together so rapidly that they emit gravitational waves in LIGO's most sensitive band. Perhaps, though less likely, there are exotic objects that aren't quite black holes in the traditional sense, which could produce subtly different gravitational wave signals. The future of black hole astronomy is bright, if such a word can be used for objects defined by their darkness. Gravitational waves have given us a new sense, a way of feeling the vibrations of space-time itself. And with that sense, we're exploring realms once thought forever beyond reach, the interiors of colliding black holes, the final moments before event horizons merge, the space-time geometry in the most extreme gravitational fields nature can produce. Every detection is a gift, a message from the universe about its most mysterious objects, and we're only just learning to read what these messages say. Closing. The universe's greatest mystery, we've journeyed far tonight. From the impossible collision that started our story, through the fundamental nature of black holes, through stellar death and forbidden masses, through gravitational waves and magnetic fields, through the vast populations of black holes across the cosmos, to the future of discovery still unfolding. And now, here at the end, it's time to reveal something that reframes this entire journey, something that connects every piece we've explored. We began with a mystery. Two black holes that shouldn't exist, detected through gravitational waves on November 23, 2023. We called them impossible, forbidden. We said they violated the rules of stellar physics. And all of that was true, based on what our models predicted. But here's the twist, the reframing that changes everything. These black holes were never actually impossible. The physics was always there, written into the equations we've studied for over a century. Magnetic fields have been part of astrophysics since the 1800s. Rapidly rotating stars have been observed for decades. The connection between rotation, magnetic fields, and mass loss was known and documented. The black holes weren't impossible. Our models were incomplete. Remember those simplifications we mentioned? When physicists modeled stellar collapse for 50 years, they had to make choices. The equations were too complex, the computational power too limited. Magnetic fields were treated as minor details, secondary effects that wouldn't change the fundamental outcome. For typical stars, for normal black hole formation, that simplification worked perfectly well. The predictions matched observations. But for stars at the edge, stars massive enough to approach pair instability, that seemingly reasonable simplification hid the truth. When Ore Gottlieb and his team finally included magnetic fields with full rigor, modeling them completely using general relativistic magnetohydrodynamics, the impossible black holes appeared naturally in the simulations, not as violations of physics, but as inevitable consequences of physics we'd simply overlooked. The answer wasn't hiding in some exotic corner of theoretical physics. It was hiding in the terms we'd set aside as negligible. This is how science actually works, not through sudden revelations from nothing, but through the patient, careful examination of what we thought we understood. Every time we discover something that seems impossible, it's not the universe breaking its own rules, it's us realizing we hadn't fully learned them yet. It's nature, patiently waiting for us to look more carefully at the equations we thought were complete. GW231123 didn't break physics, it revealed physics. Those two black holes, spinning at nearly the maximum rate, merging 7 billion years ago, were teaching us something we'd missed. The universe was giving us a gentle correction, like a teacher marking a student's work. Close, it seemed to say. But you forgot something. Look again, more carefully this time. And here's the beautiful part, the part that makes this story more than just an astronomical discovery. This pattern repeats throughout the history of science. Orbits that violated Newtonian gravity turned out to reveal general relativity. Stars that shouldn't be where they were turned out to reveal dark matter. Galaxies moving in ways they shouldn't revealed dark energy. Every impossibility has, eventually, revealed new physics. Black holes are not just objects to study, they're messengers. They're the universe's way of showing us the boundaries of our knowledge, the places where our theories need refinement, where new understanding waits. Every forbidden black hole is actually an invitation. Come closer, look deeper. There's more to learn. The singularities hidden behind event horizons, forever sealed away from direct observation, might seem like the ultimate frustration for scientists. Information locked away, physics breaking down, mysteries that can never be solved. But from another perspective, they're promises that there's always more to discover, that the universe will never run out of mysteries, that no matter how much we learn, there will always be another horizon to reach for. We are, in a very real sense, children of the cosmos. The atoms in your body, the iron in your blood, the calcium in your bones, the oxygen you breathe, all were created in stellar furnaces and scattered by supernova. Some of that material might have passed close to black holes, swirled in accretion disks, been shaped by gravity billions of years ago before eventually finding its way into the gas clouds that formed our solar system, our planet, us. And now, billions of years later, Some of those atoms have arranged themselves into patterns complex enough to wonder about black holes, to build detectors sensitive enough to feel space-time ripple, to solve equations sophisticated enough to predict how magnetic fields affect collapsing stars. The universe is studying itself through us. As you rest tonight, as sleep comes softly and the day's thoughts fade, remember this. The black holes we called impossible weren't defying the universe. They were showing us a deeper truth about how it works. And somewhere out there, at this very moment, other mysteries are waiting. Other impossible things are happening, ready to teach us something new. The universe is not just vast and mysterious. It's generous, patient. Every time we think we've reached a wall, every time something seems impossible, it's really just an invitation to look more carefully, to question our assumptions, to find the piece of the puzzle we overlooked. GW31123, those two forbidden black holes spinning through space 7 billion years ago, were never breaking rules. They were following rules we hadn't fully understood yet. And by finding them, by measuring them, by wrestling with the mystery they represented, we learned something profound. Not just about magnetic fields and stellar collapse, but about the nature of scientific discovery itself. There are no impossible black holes. There's only incomplete understanding. And every time we close one gap in that understanding, the universe reveals 10 new mysteries waiting behind it. That's not frustrating. That's beautiful. It means the journey never ends. It means there will always be more to wonder about, more to discover, more to learn. As long as there are mysteries, as long as there are black holes and gravitational waves and questions without answers, we have purpose, we have direction, we have something to reach for. If you've enjoyed this journey through darkness and discovery, if these explorations help you find peace or spark curiosity, consider subscribing to Sleepable Science. There are so many more mysteries to explore, so many more cosmic stories to tell. Until next time, sleep well, dream softly, and know that the black holes that seemed impossible were really just patient teachers, waiting for us to ask the right questions. The universe is singing, in gravitational waves and starlight, in the dance of galaxies and the collision of black holes, and we are learning slowly to hear its song. Good night.